Yeah, and again, the trick for the proof is to be found in Kuratowski-Mostowski at a rather hidden place, and I have found no other book where this trick is mentioned. On page 17, I guess. Okay. Yeah. What to do with this situation? That is to say, with these topological strange formulas that up to now have more or less completely ignored by philosophers, and which are in urgent need of philosophical explication. So we finally end up in the following theory. Or let me mention just another fact. The common sense formula that the boundary is boundary applies to a certain subset of sets, namely to those subsets whose interior is empty. And again, this form a Boolean algebra, but a non-complete Boolean algebra with respect to set theoretically intersection, union, and negation. So here we have another order structure, namely this Boolean algebra, which is almost completely unknown, but was already invented or already found by Stone and McKinsey, that may have interesting Mereological applications. No, which? Yeah. So, if we consider this space of this space of possible worlds that we started with, then the boundary concept is rather well behaved. For spaces which satisfy this condition, for instance, open sets, closed sets, intersection, and many others. And these are not precise, recall, vague concepts are concepts the boundary, whose boundary is not empty, which have borderline cases. It maybe a concept may have borderline cases, but the set of borderline cases has an empty interior. That is to say, the set of borderlines is rather small, and we can restrict our logical considerations onto this sort of concepts, which empty interior. So this may be defined as rather precise, not really precise, but rather precise. And then it turns out that concepts who have an extension that of this kind are the interior of which is not closed. So we have classification of concepts according to their behavior with respect to borderline cases. The precise ones are those that are clopen, that have a zero boundary. The rather precise ones are those the interior of the boundary is empty, and the wild concepts, examples like Q, something like this, where this does not hold. Yeah, and this is a classification that can be carried out only in topological language. So this is, one may say, a progress beyond the only set theoretical language.
Just a small comment in the interest of clarity. There's a typo, I think, on the slide. This int and if and only should be switched, just in case someone is confused. Yeah, like if and only if int boundary of A equals the empty set in the main formula.
Yeah.
Yeah. This exactly. If
yeah, you are right. This should be there.
I got confused at first. I
yeah.
Read the formula.
Sorry. Yeah. So this standard equation holds only for, so to speak, well-behaved concepts, namely concepts that have whose the interior of the boundary is empty. No, I mean other questions? It should be.
I was wondering, when we didn't do the section on variability and falsifiability of epistemology 1, is there a similar kind of classification using the boundaries?
Yeah, falsification and refutability. No, this is falsification and refutability does not deal with boundaries, but does deal with closure problems. So.
It's okay.
No, it's quite interesting. It's of the same kind. We have a kind of we have a space of logical possibilities, and then topology attempts to clarify the notion of scientifically reasonable concepts. And according to Popper's theory, a hypothesis is only a reasonable, scientifically acceptable concept if and only if it's falsifiable. So hypothesis inside the logical possibilities of some experimental science is just a set where it obtains and the complement and where it does not obtain. An experiment or a reliable experiment is defined as an open set, because the openness is forced by the idea that experiments are never precise but only approximately. So let us assume that the hypothesis should figure as scientifically reasonable concept hypothesis, then it may be falsified in this way, because outside the hypothesis I can already find a small open set that remains totally outside the hypothesis. This is simply the case because if H is closed, then the complement of H is open, and we learned that if a set is open, we can always find a small neighborhood that still belongs to the open set. And this small neighborhood symbolizes the vagueness, or the or one may say the stability of the experiment. If an experiment would take place here at a boundary point, I've never a certain result, because a small variation may lead to confirmation and to refutation. But here this is not the case. A small variation of the experiment always stays outside the hypothesis, so it refutes in a stable way the hypothesis. But now comes a certain sophistication. The authors, Schulte and Uebel, show that there is another topological explication of scientifically reasonable, namely a hypothesis is scientifically reasonable if and only if this is a definition of nowhere dense. This is almost at the edge of what we learned yesterday. And the problem is that there are nowhere dense subsets that are not closed, and there are many closed subsets that are not nowhere open. So topology offers us a refinement of the idea of refutability that points in different directions, and in common sense or set theoretical considerations, closeness and nowhere denseness are not distinguished.
I have a quick question.
Yeah.
Quick question. So, okay, suppose that we have a set with a finite number of elements, finite set. Can we generally say what its boundary would be? What is the boundary of a finite set of elements?
The boundary, this is trivial.
Depends upon topology. Depends upon topology. Okay, so let me rephrase the question. Is there any sort of interesting non-trivial topology that would assign, like I said, some boundary to a finite set of elements? Now, the reason I'm asking this question, of course, this is kind of like a loaded question, but it has some sort of hidden assumption. The reason I'm asking the question is that because you're trying to apply topology to the problem of vagueness.
Yeah.
But my understanding is the problem of vagueness works, or it should work, under the assumption of finiteness of extensions of ordinary concepts, such as being red or whatever. I mean, we can easily assume that there's only finitely many red objects in the universe. So and you're of course using tools, topological tools, which strictly speaking presuppose continuity, things like that. So how can you apply these tools to problems which sort of are based on the assumption of finiteness?
I would answer in the following way. Here I have always implicitly presumed that reasonable topologies are T2 topologies, Hausdorff topologies. That is to say, as we learned yesterday, 2 points can be separated by two open sets. But for finite sets, Hausdorff topology is trivial. So if we want to deal with finite sets or more sophisticated applications, we should go down from T2 topologies. Yesterday we moved up from Hausdorffness to higher topologies, to stronger topologies. But in recent studies, so in the last 10 years or so, the interest moves from T2 to weaker topologies. So here we have T1, here we have sober topologies, and a lot of other ones. So people are eager to invent their own topologies. And then it may, how for these topologies, the...
Sober is weaker than okay. Sorry.
So here we end up with rather catastrophic spaces T0 that satisfy a very minimal assumption in order that topological considerations make sense, but the domain of activity is somehow here, between or up to here, this below T2. And I know nothing about problems of how the boundary operator behaves below T1 or T1.5. It should be interesting, to study for vagueness topologies that are strictly smaller than T2. But up to 1960 or Kuratowski only deals with T2. This is classical topology.
So my understanding is that you were trying to derive some useful lessons about the notion of the problem of vagueness from considering topologies of T2 type. And
not necessarily. I mean, I say the closure operator, so being located here, can be replaced by boundary operator. But of course, this holds for every topology. But then how this boundary operator for the very weak topologies behave, I have not studied, and I think nobody.
It's like an open question. Okay.
So this is a field for further research. What is the outcome if we reformulate topology in terms of boundary? But the point that I want to make now is simply we can start with a boundary operator. So we can say topology is a theory of vagueness. Because vagueness occurs depending on what borderline cases A has. If we want to live in an absolutely exact universe, then this mapping is trivial, and everything,
Yeah, but again, from a philosophical perspective, I mean, this is like a sort of this is like a supposition that we already have. Like we have to sort of show that this can be done given the assumption of that we have a finite universe. Because I mean, otherwise we would have a theory which, I mean, theoretically you could probably model using a sort of a theory that somehow refers to infinite objects. You could try to model finite reality, but it would be kind of like unnatural to do this. So my point, which I'm trying to press here, is that this is kind of like a sort of like an open road ahead of us. Like we can follow this road, but we still don't know how to do this, as far as I understand.
We should study. We should generalize these considerations to more general topologies. T2 was only a classical starting point, nothing else.
But from a philosophical point of view, one can say that if you want to model some, let's say, a finite universum, we can model this universe by finite models. It is not, why? Because we can see more with this, let's say, this infinite model.
Yeah, but in this particular case, it would be strange because it seems that there's like an intuitive interpretation, like you have presented this. What is an extension of a predicate? It's just a set of objects that satisfy the predicate. So it's kind of unnatural to me to use a theory, which just assumes the existence of infinite sets and say, and by the way, actually, the sets that we're talking about when we speak about, extensions are actually fine.
Okay, there's a lot of work to do, and I did only the most modest and most primitive ones. So let me conclude or come back once again to Stone and his maxim: you should always topologize. Okay? What's the task? The task is to topologize structures in such a way that these structures are represented in a useful way by topological spaces. So we should invent, so to speak, a topological space for a certain structure in order that this topological space reflects important properties of this structure. The first example where this was carried out in a non-trivial way was Stone's representation theorem, proved in 1937. So, and what Stone did was to relate the theory of an algebraic structure, namely the theory of Boolean lattices, with topology. As it seems, and most people believed at that time, was that these two theories, or one may say these two categories, have not much in common, because the Boolean algebra is algebraic with certain operations of conjunction, union, and intersection and negation, while the topological space is something continuous. And now probably most people had the idea that topology has something to do with rubber geometry. What has rubber geometry to do with Boolean algebras? So then the task of Stone was to invent a topological space that represented in a useful, non-trivial way this algebraic structure, namely the Boolean algebra. What does it mean? This means to invent a set of points and to invent a topological structure on this set of points that represents the algebraic structure. This sounds a bit abstract, so I want to start with a concrete example, namely with the Boolean algebra. We already know the power set of some set X. And here we have already some ready-made points. Yeah. No, wait. Some ready-made points that somehow belong to the Boolean algebra Px, namely the points of X. Here it seems points are already available. We have the algebraic structure and we have the set X. And the problem is to express somehow the elements of X in algebraic terms. So a point should not be simply over there, but a point should be a sort of operator. Again, this operator perspective. And here it is rather easy, namely A defines an operator of this kind. An operator defined in this way, we have the most simple set, the simple set possible, namely a set of two elements, and a point corresponds clearly to a homomorphism or to a morphism between Boolean algebras. This is the smallest Boolean algebra, namely applied to a certain A, the value is 1, and the value is 0 if and only if A so try to calculate the function HA for applied to A. According to this picture, this means HA is 1, but HA of B is 0 because A is not contained. This is called in mathematics the characteristic function. Okay, so a point A and X defines a mapping, namely this simple mapping. And different points clearly define different mappings because different points may be distinguished by different neighborhoods. Yeah, this can be applied in the special case of power sets because we have available already the real points. But the great idea of Stone was that a point may be defined not only in this way as an element of a set, but as a homomorphism. Homomorphism is algebraic morphism. Points may be elucidated functionally as homomorphisms of the algebraic structure mapped to the two-point sets. This was called 2. Yeah, question. So let us assume, or clearly we have shown that every real point defines a functional point by this recipe I just gave as a characteristic
A in X, not A in the power of X.
No, also what I want to say, there's no PowerPoint available. A function corresponds to a homomorphism of this kind, to an algebraic mapping. That is to say, a point is a sort of action, namely mapping the subsets of X either to 0 or to 1, depending whether the point is contained in the set or is not contained. This is nothing but a complicated round-the-way definition of a point. But it has one great advantage. It can be applied not only to this sort of very special Boolean algebras, but to any Boolean algebra, regardless whether this is a power set or some other stuff. So the proposal is generalized points are homomorphisms B. And this is a great idea. It looks trivial or elementary, but it allows us not only for Boolean algebras, but to a lot of other algebraic structures, lattices, order structures, whatever, to invent points. And if we are able to topologize this set of points, then we have a more or less faithful picture or image of the algebraic structure. And this helps us. So we study only the topological space resulting from this definition of general points and try to draw conclusions that are relevant for the original structure. And this is called in mathematics spectral analysis. Probably has nothing to do with physical spectral theory, but this has emerged as one of the most fruitful general recipes for applying topology to other mathematical structures. It is rather difficult and needs a lot of ingenuity to define the topology, but at least you may have an idea of what the points of the stone space are. You start with a Boolean algebra, and the stone space of this Boolean algebra is defined as the set of homomorphisms endowed with stone topology, and the great result, a surprising result of stone was that this is a absolutely faithful correspondence. It does not matter whether you study Boolean algebras or whether you study Boolean spaces, and this can be generalized to not only Boolean algebras but general algebras, and the outcome is that actually you can start Heiting algebras. So yeah, in this way, you have the topological space, you forget about the points, you keep the algebraic structure, you invent points for the algebraic structure, you topologize, and you end up where you started. So there's a full equivalence between topology, good topological spaces, not for all topological spaces, but good topological spaces, and have good Heiting structure, and so this shows equivalence between two quite different, apparently quite different categories. Yeah, and this is Stone's representation theorem that has been generalized in the last year immensely to many, many other structures, and a successful example of how to topologize mathematics in a quite literal, precise sense. Thank you very much.